박수 부탁드리겠습니다.
Thank you. Good afternoon. How's everybody? Good? All right, so first a little bit of history from DuPont. So DuPont started in the 1800s, 1803 to be exact. And what happened was that the DuPont family came to the United States as land developers and also to make gunpowder. So we were in the explosives industry for over 100 years. And what DuPont did was they started to want to build better explosives, so we got into the whole science, basic science, and got into polymer science. And what really was put us on the map was in 1935, DuPont actually invented nylon. We went on to invent a bunch of different materials. You probably are familiar with Lycra and spandex and materials like that. Well, we sold off that division. That's actually, those trade names belong to another company now. But we've invented things like Tyvek, Nomex, Kevlar. We're here to talk about Tyvek. Kevlar was used in ballistic applications. Nomex is what the firemen wear. And for example, the first spacesuit that went into space, landed on the moon, it consisted of 22 layers. 17 of those layers were made with DuPont materials. And so last September, Dow and DuPont merged into one company, so we're now part of a single large company with the sole purpose of dividing up into 3 separate companies. So the first company is the Ag Group. You can go to the next slide. And the Ag Group is actually going to be about a $14 billion division. These are some of the things that we actually do in the Ag division. You probably ate something today that was made by DuPont. And then the second division that's going to be spun off is going to be about $40 billion in sales. And this is basically the legacy Dow business, which is all of the polymers and films and material sciences. So this will be its own separate group that'll get spun off. And then finally, the third division, which is going to keep the DuPont name, is the Specialty Products Division. We have a group that does and focuses on the electronics imaging area, another one in the polymers, safety and construction, which is what we're under, and nutritional biosciences. To give you an idea, in the photovoltaic market, for example, we sold over $1 billion worth of paste and films that make solar panel work. We also have components that your phones, if we did not invent, your phone would not work. The TVs that you use, the plasma or LCDs, we've invented components in there as well that would not work if it wasn't for DuPont. And to give you the final kind of famous one that you may not know of is the inkjet printer, the cartridge and the ink and the technology behind that. We invented that. You actually pay DuPont a royalty every time you buy one of those little cartridges. Okay, so we're going to be a $21 billion company and nothing changes. So as far as you're concerned in terms of the delivery and receiving of Tyvek, from our perspective, not a single employee changes, nothing, it all stays the same. Okay, so let's talk a little bit about how a breathable material, right, can allow air to gas to pass through, and yet at the same time not allow water to go through and or, in this particular case, bacteria when it comes to medical devices. So in order to talk about this, we have to step back in time and we have to talk about a guy by the name of Louis Pasteur. Okay, Louis Pasteur lived in the 1800s. And back then, they did not have microscopes. They did not know about viruses and bacteria. What Louis Pasteur postulated was this. He thought there was something in the air that was making people sick. So he came up with this experiment to prove that there was something in the air making people sick. So he had this flask and this bend in the flask that was open to the air. Okay? So what he did is he boiled both of these, right? And today we know that as pasteurization after his last name, when you boil something and you kill off all the bacteria, right? And then what he did was he actually cut the end of the flask off, and then the stuff that was in the air came in and contaminated. But the other one that was still open to the air, through the tube, did not get contaminated. Okay? This proved that there was something in the air that was making people sick. Okay? So this experiment happened in 1863. So I have a question. This is group participation time. Question. If this particular experiment, the flask, was still around today, would it still be clear? So how many people say yes, it's still clear? How many say no?
상했을 것이다.
Oh, no's. We got a lot of no's. Any yes? Okay, we got one yes here, 2 yeses. Okay. And the answer is yes. If you go to Paris, France, there's a museum called the Pasteur Institute. That is an actual picture of the flask itself. This is a picture, and those are the actual bends. It is still clear. Now, what does this have to do with medical packaging? And it's this. Bacteria and viruses always move with the flow of air. Okay, they don't have wings. They can't go against the flow. So if the flow of air is coming like this, what happens is it's going to come, it's going to impact, and it is going to stop on the surface of, this is actual Tyvek, on the surface of Tyvek and stop there. Because of electrostatic forces, it's going to stay there. If, perchance, it falls off, it will fall on the next one. And if it falls off that one, it falls on the next one. So those bends create, in English, what's known as a tortuous path. Okay? Every breathable material creates a tortuous path. They're not all the same, they're not all equal, but they create a path that's tortuous that makes it very difficult for the bacteria and viruses to make their way through. So another way to think of this is that certain materials have more of those bends in it than other materials, which make it harder for bacteria and viruses to make their way through. Now there's a standard out there called the ASTM 2638. And in this particular standard, what we're doing is we're going to take 2 million 1 micron sized styrene spheres, and we're going to put it in this machine, and up there at the top we put the styrene spheres. We have a sample in here, and on the bottom here we have a particle counter. So we're going to count how many of those 1 micron styrene spheres made their way through the material to the other side. So several years ago, there was a couple of people by the name of Sinclair and Talentire, and they actually did this study, and what they postulated, what they figured out was that bacteria, viruses act like particles. Okay? So instead of embedding 2 million bacteria up there, we're going to embed 2 million particles. It's just cleaner, healthier, and safer to do that. Okay? And so we can see here that all these lines down here near the bottom, they're near 0, is Tyvek. So 1073B, 1059, and 2FS, they actually are 0.5, 0.6%. Here, the first one that you see here is actually 55-pound coated paper, and up here you see 40-pound uncoated paper. So those particles have a point at which you're going to maximize the amount of styrene spheres that actually flow through. Here with Tyvek, they're pretty much 0 and stay 0 across the range of airflow. So if I have a pouch and I am going to just hand it to you, right? That happens to be 1 centimeter per minute. Okay, this motion right here is 1 centimeter per minute. And you can see that 1 centimeter per minute is right in that range where at paper it's the highest point of ingress for those particles. Okay, and the reason for that is this. On the next page, what you'll see is that the particles, or the fibers of paper, are of a given width and length. Right? So if you go and buy paper at the supermarket, you get the shopping bag. It's a very large fiber, very thick, that makes it strong. Kleenex is very small and tiny fibers, right? That's why when you pull out that Kleenex, you see the cloud of dust, right? Those are the small particles coming off the paper. Medical grade is neither big nor small. It's of a certain size, so it's strong enough to withhold, right? But at the same time, the fibers are all of the same thickness. And as you can see, there's the same thickness and size, and so there's a larger gap in between, and that's where particles can make their way through. Tyvek, because of its multiple layers, creates a tortuous path and is much more efficient and effective at actually keeping particles out or bacteria out. Okay? And we can talk more about microbial barrier later on a one-on-one level. So let's talk a little bit about how Tyvek came to be. Oh, no, wait. First, let's talk about Tyvek. It's ETO. steam, E-beam, gamma, and sterad, all of these different radiation forms or ways of sterilizing something, Tyvek is completely good with all those forms. Okay? So, question for you. What are we trying to do when we sterilize something? What is our end goal when we're trying to sterilize something? Come on. What are we trying to do? We are trying to make that microorganism sterile. Okay? And I want you to understand the difference, right? I can take alcohol and I can disinfect this table. I can kill the bacteria. But I may or may not destroy the RNA and DNA. So when I'm sterilizing, I am trying to destroy the RNA and DNA and prevent that microorganism, right, from being able to replicate. We want to make it sterile. Okay? ETO is wonderful at unzipping the DNA chain. Gamma and E-beam destroy the RNA and DNA. Steam explodes it and actually breaks apart the RNA and DNA chains. And same with the oxidative state of sterad or hydrogen peroxide. Okay? Just a note for yourself. When we're trying to do sterilization, we're trying to sterilize those things. We're trying to make them so they cannot replicate and reproduce. All right, so how did Tyvek come to be? How did we figure out Tyvek? Well, there was a pipe running through a lab, right? And the fitting actually developed a crack right there. And then out of it flowed polyethylene onto a lab table. The next day, a guy by the name of Jim White walked into the lab, saw this stuff coming out, and looked down onto the lab table, and he thought, I can do something with that. That was 1955. Okay? So in 1959, we actually built a small machine to actually make a web width of that material. And then finally in 1967, line 1 was produced. Our very first line was built. It is a 10 feet wide web. It's over 3 meters wide. First time we made Tyvek in 1967. And then the first time it was used in medical packaging was in 1972. Can anyone tell me what grade of Tyvek that is that was first produced in 1972? Anybody? Anyone? It is 1073B. Okay? So 1073B has been around for 46 years. We haven't changed anything. Okay? When they made it perfectly. It was the right thickness. It was the right microbial barrier, had the right flexibility, the right surface characteristics. They actually got everything perfect with the very first product. Everything since has been a compromise. But 1073B, since 1972, for 46 years, we've been making it the same exact way. And the polyethylene is FDA approved for food contact. Okay? And because it's so pure, right, the material is so pure, we don't use reclaimed, we don't use recycled, we don't use regrind, we use virgin polymer when we make medical grade. And because of that, it's actually the best thing to recycle. You can recycle Tyvek because it's so pure and clean. Now, there's 3 things that we do not do with Tyvek. We do not corona treat, okay? So this next picture is not a corona treater, it's actually a plasma treater, right? So you can see here, this is a plasma treater. Underneath here, you would pass the web of Tyvek or you would pass the web of a film. Whenever you pass an electrical arc across the surface of a plastic, what you're actually going to do is you're going to rip off one of the hydrogens right off the polymer and you're going to leave it negatively charged. Another word for saying that is you're going to ionize the surface. Inks bond ionically. So if the surface is treated, it will be ionic. And now you have great adhesion. So the graphics grade, some of the other grades that you see do wonderful bonding because you surface treat, okay? But for medical packaging, we do not turn this on. Why? Because you can think of this as little lightning bolts. And if you have an arc that is too powerful, it will actually go right through the material and induce a pinhole. So we don't do this for medical grade Tyvek, okay? So the printing that you'll see will be simple. It'll be 1, 2, 3 colors max. Very simple printing. You can still print well on it, but it's just not going to be as good because we do not surface treat it with corona treatment. The other thing we don't do is what's called adding a UV additive. The frequency of ultraviolet light, right, is such that it will break down a polymer. So if you remember being a little kid and you bought some cheap toy and you left it out in the sun, right, it would turn white or would start to break down. That's because it either did not have a UV package in it or enough of one. So if you take medical grade Tyvek and you leave it out in the sun for a month, it will start to turn powder. Medical grade Tyvek will fall apart. Some of our other grades have that additive, but we don't. Now, we don't believe anybody in the medical industry will leave their product out in the sun for a month, so we don't think this is an issue. We don't put this in there because that additive could contaminate a medical device. And finally, the last thing is anti-stat. Now, an anti-stat is nothing more like a soap, and soap is this wonderfully unique molecule in the world, okay? Because soap, at one end, we bond covalently. At the other end, we bond ionically. So when you take a shower, right, we all know that oil and water don't mix. But what soap does is one end will attach itself to the oils into your skin, and then when you take a shower, the other end will attach itself to the water, and that's how you get clean. Super unique molecule in the world. It's also another name that it's sometimes referred to as a surfactant. Now, when you put it onto a plastic, what it does is it will attract moisture from the air to the surface of the material. You then have a localized humidity, and thereby you don't have a static charge that can build when you have localized humidity. So that's what an anti-stat does. An anti-stat brings moisture to the surface of the material to prevent static charges from building. Because we don't put this anti-stat in there, it's very important that you control humidity in your process and in your operations. In automated systems, for example, you have to have enough humidity or else the lids will stick when they transfer to one another, okay? If it's too dry, the other thing that can happen is that the Tyvek acts like a magnet. It will actually attract dirt and particles from the air right to the surface. It literally just attracts it, right? We get complaints, oh, Jose, Tyvek's dirty. It's not dirty. You can have issues associated with the static being so high that you're actually attracting to it, all right? So you want to control your process with a certain amount of humidity in those rooms so that the Tyvek is not supercharged to the point where you're attracting dirt or you're causing issues. Okay, so we make 3 grades of Tyvek currently. We're going to talk about the 4th later on. We make 1073B, 1059, and 2FS. The original was 1073B. Years later, we made 1059, which is thinner, and years later, we made 2FS, which is thinner. The difference here is that this has titanium dioxide, so it's whiter. The only reason we add that additive is to make it whiter, but those are the 3 current, well, we have 4. We'll talk about the next one later on. Okay?
Okay.
Perfect. Thank you. Arik.
감사합니다.
감사합니다.